what I want to do, I want to make sure that there is no confusion between the Higgs and the Goldstone mechanism. So let me now make a summary of essential features of both of these, okay? And in the process, we'll actually do some more physics. We are going to now concentrate a bit on the Goldstone, not so much because it's a part of the Standard Model. There is no Goldstone boson in the Standard Model, but because it's a very interesting physics that touches upon the Standard Model, and you will often hear about it. And notice the way I did it. Normally in the books, if you have a look, people first teach the Goldstone mechanism, which has nothing to do with what we are doing. Just sort of to prepare you. I did it in a funny, strange way. I did it upside down, sort of. I studied with the Higgs for you to appreciate that when I turn the gauge field off, that I do recover this thing that I have taught from the beginning. Okay, I did it because I remember when I learned it at the time, it was not, you didn't learn it in a course, okay? It was just the very beginning. So, of the field, I was sort of bugged when I learned the Higgs, you know, where is the Goldstone? When I take the limit. And remember that we saw it explicitly, I remind you. So let's start. We exemplify everything on the U1 case. If you understand U1, I don't care about group theory. You know what goes on. Okay, so we took the Higgs, which I can write as a U1 symmetry emphasizing A, that he has a gauge field, and Lagrangian would be d mu phi square. I'm writing now symbolically, I wrote it many times, minus, no, let's write first the kinetic pieces. Some, whatever are my fermions in the theory, psi bar, gamma mu, d mu phi. Okay, psi stands for any fermion I can think about. Okay, there may be 25, okay, there may be 1 as in this example. Then, of course, there must be interactions in the form of the potential for the scalar field, and there must be Yukawa interaction. I could write it as a V Yukawa, L Yukawa. And of course, gauge field propagates too. I can write like this for simplicity. F squared, just to write immediately, okay. In the Goldstone case, I could call it UG. It's global. Lagrangian basically the same, the only difference there is no covariant derivative, right? So in this case, and notice that these two pieces are of course the same. There is no derivative here, so there is no reason even to think about the possibility of distinguishing the two. Okay, this I have completely the same interaction. This is very important. Like Higgs Lagrangian. In our case, d mu is generically QA mu, whatever the coupling of the charge is. Notice that there is a freedom in renormalizing charge any which way I want by reabsorbing it in G or vice versa, okay. And then in our example, I took a left-handed fermion psi L, a right-handed fermion psi R, and of course phi, with charges QL was equal to Q phi was equal to 1, and I took QR equals 0. Notice he gave us complete analogy with the Standard Model later on, in which the right-handed particles are singlets, they don't couple to the gauge fields. The potential, which I can write here, I can create a common region, the potential and Yukawa as a Yukawa coupling, psi L bar, phi psi r, that's Hermitian conjugate. I may sometimes forget to write Hermitian conjugate when there is a complex situation. You of course will remember it. Okay, I may be careless or may simply don't want to emphasize it. Okay, so this is common to these two theories. The only difference, of course, is because of the gauge interaction. I need to put the covariant derivative. So what I mean here, when some field, when I say that it's gauge, which any field F will transform as e to the I alpha q, you can put F if you wish to emphasize, of that field. And in our case that we are studying here, alpha is a function of x. In the global case, alpha is constant, by definition. What we learned from the covariant derivative, what it gave us, okay, let me summarize the essential features. That due to the gauge freedom, okay, the first statement I should make, I can write that phi is 1 over square root of 2 v plus h. Why? Because the phase, there is a phase here, phase cannot be physical, so I simply gauge it away. Okay, what we say here, that we gauge away a piece, we would have the phase e to the ig over v, or you rotate away, you get rid of it because of the original gauge freedom. Okay, and this gives us, and this is a celebrated Higgs field, Higgs boson, which has basically the same properties as the Sander model one. It's all captured here. And remember what we got? We got that gauge field has a mass proportional to the only scale of the theory. V. The fermion gets a mass, which is Yukawa. I think we get over square root of 2 because of the normalization. Right. And we find the celebrated Higgs coupling, they are always proportional to mass. So you will get G MA, A mu, plus G M fermion over MA, phi bar psi. This is basically all you have to remember. The theory is very simple. It's hard to say what is simpler. Well, there is a gauge field, so you may say there is additional complexity, but the scalar field is simpler in this case. I managed to get rid of the degree of freedom. Here I can't do that. So in the global case, see, I can put an index h if you wish to special. In the Higgs case only I can get rid of g, not in the global case, of course. I have no right to do the gauge transformation. Please remember that Higgs exists even in the non-Higgs case. In the Goldstone case, or maybe what we should say Nambu-Goldstone case. Actually, Goldstone was aware. That's the field that accompanies the vacuum exponential value. That's the field responsible for the masses. In the Higgs case, the only difference is it gives the mass to the gauge boson because it exists. In the Goldstone case, there is no gauge boson, we can't give it a mass, but it'll give the mass to whoever it couples to. Okay, there is this basic similarity. Please pay attention. That this is common to these guys. And the novel thing is, of course, the existence of G, and we said it has to exist. It was just the original degree of freedom. I have two complex degrees of freedom. The two important characteristics of this guy that is called Nambu Goldstone boson or Goldstone boson. It has to be massless. That's a degree of freedom. It actually has to do with the phase, right? If I expand the phase, then I gauge the weight, I will get this G. So I'm reading off its essential property, mg is equal to 0. It tells you that there is an equipotential surface, which is a circle. Okay, we can write here that in this potential here, m0 is a circle. M0, remember, is this vacuum manifold. Mg0, and equally important, it has an interaction which there was a factor m, well, sorry, no g. There is no gauge field, I shouldn't talk of g. E M fermion over V G psi bar gamma phi psi. Follows immediately from here. No, from here. H gives me the another way to remember is this is actually M fermion over V. You can write your Higgs interactions any which way you want. Okay. This may be a useful notation because this is valid even when the gauge field disappears and gauge coupling goes to 0. But it's equivalent. In this case, this is of course the correct way to write it because there is no gauge field. So notice that the coupling is axial. And we should talk more about it today. But before I turn more to the Goldstone case, let's just summarize the question that Julian posed. Why don't I produce this guy? Okay, I sort of try to show why not, so let me be a little more detailed and a little more careful. Why is it that this guy doesn't really exist? Okay, I try to offer various reasons. Okay, so let's talk a little more. Because, you know, here I was very smart. It wasn't easy to figure this out. Naively, you have written it as a complex field. I'm sure, you know, if you don't spend a lot of time, you know, pondering over that, okay, the natural thing is to write what you had. So maybe I should say here, this is called the unitary picture. I mean, I should say, I should write. We say this very often. And then there is an arc side, renormalizable, gauge or picture, where I actually keep G. Well, I know it cannot be physical. I know I counted degrees of freedom because when I gave the now Proca field, the gauge field, which is not Maxwell anymore, the mass, is 3 degrees of freedom. So there cannot be 2 degrees of freedom. So what are the characteristics here? The importance. First, that in this gauge, the propagators, so let's start with the G field, tells me that the guy has a mass which is proportional to the gauge fixing term. I'm allowed to take any value from C. I can take it to infinity. And I see immediately that I get what I wrote in the unitary gauge. Okay, that already tells me it can't be physical. In the same gauge, d mu nu is d mu nu Proca. The physical, let's write it here. D mu nu Proca, passive gauge field, is minus I G mu nu minus Q mu Q nu over ma square Q square minus ma square. There is a Proca piece and then there is minus I Q mu Q nu over ma square Q square minus phi ma square. Notice the same patient pattern. This is very important. Okay, so I'm propagating something that doesn't really exist, obviously. This can be always turned off. At any point, I can decide that I don't want to live with these guys by taking psi going to infinity. If I do keep it, I notice immediately these guys, of course, cannot, I should not even ask the question how to produce them. They don't exist. They are gauge-dependent quantities, which in the unitary gauge simply go to 0, okay? But if I keep them, okay, it's good to remind us here, this I could have written as I over Q square minus ma square sigma epsilon mu star. the sum of the three physical degrees of freedom. This is how you can derive the propagator, equivalently to the just inverse of the quadratic form, right? What is the propagator? It's the famous Clyde-Gordon. I see some puzzlement there. Sorry? There is no question. No, there was. I was looking at you guys and I see somewhat puzzled faces. So I'm. We agree with this? Yeah. All of us? There's no confusion here. Not 20 minutes after I started. Okay, this simply tells me that each of these guys propagates as Clyde-Gordon. There is no other way of propagating. Fermion propagates the same way. All you have to do is sum these guys, okay? Because this simply is the inverse of the quadratic form, which has to have this form. Einstein told us, when I'm a shell, I have to get q squared equal ma squared. Of course, q squared is not equal ma squared virtually in the loop, okay? According to Mr. Feynman. And this is the celebrated formula of the physical degrees of freedom. If you would like to keep this, you say, well, let me see what happens if I want to keep this physical picture. What would I get here, for example? I would get here, well, then I should be a little careful. Then I should write this extra piece. This extra piece here, I put it in a bracket. Notice that I should write here I. I always want to emphasize this I. This is our convention for the Klein-Gordon, or what comes out by inverting the kinetic energy. So I want to have I q squared minus ma squared. I have to then think of the propagation of the physical particle, right? What I will get here is minus q nu over ma squared times q squared minus ma squared minus ma squared divided by q squared minus psi ma squared. Then I stop here. And see if you have followed what I said. I said only extra piece. I just wrote it. I did nothing. I divided and multiplied by q squared minus ma squared, and I took care of the signs. To emphasize that there is a strange sign minus here, this is very important. And to emphasize immediately this question that we can call it Julian's question, okay, that Bachin, I shouldn't worry about producing this guy. Go on shell. This is what you mean by producing. This disappears. This never really propagates physically. It propagates inside the loop because there I am allowed to do whatever I want. I found anything that is useful for me to do the calculation the way I did in QED. I'll be more explicit, okay, but already here I suspect that I'm completely okay. When q squared is ma squared, which is a physical particle, right, this extra piece goes to zero. It stops propagating. So I'm not going to be able to produce it. Extra degrees of freedom become zero. Same here. Notice I can write this. You understand, because here there is an extra degree of freedom proportional to q mu. There is yet another degree of freedom. This is actually a part of the same gauge field, okay, Stuckelberg. Remember how we did, which Stuckelberg guys did, by adding this degree of freedom. This I can write as I over q squared minus ma squared. Notice I'll get the same piece, q squared minus ma squared by q squared minus 5 ma squared. So if I keep this psi, okay, 1 second for, if I keep this psi, you know, I have an advantage to read off immediately that on shell I don't even have to worry to go to the unitary gauge, and then I let it go fast.
But the psi is 1?
Sorry? Yeah, precisely that. what happens if, okay, now comes the devil's advocate, he says, okay, you convinced me, but what happens if psi is equal to 1? I won't see that. So let's treat that, which we actually will happen in general, but let's do that case because it's not really obvious. Just to satisfy it, okay? You see now the question is growing, okay? It's not just for the end, it's for, it says, okay, I really want to see what goes on, okay? Well, please notice here that they have the same factor. This is very important. The only difference is that here I'm adding a scalar degree of freedom, notice precisely, coefficient to 1. Here I'm adding this time-like, what I call, precisely proportional to, actually will be I q mu. As if epsilon mu is I q mu, I get a minus sign, right? Okay, we'll write it carefully. So we'll have to create some space here. So let's steal from Boson and then come back. But in order to answer this question, okay, because it's somehow as if you haven't done it, okay, let's see what happened in QED, because it's a similar question. You shouldn't be asking me this question. You should be asking this to Saif. You should be asking me what happens in QED. Right? You said, wait, think about it. It's the same situation that you faced before, a few months ago, or I don't know, a few weeks ago. There we also had extra 2 degrees of freedom. So let me remind you what happens there, and then I come back to this. In QED, look, what I mean, I don't even have to answer this question. I can say, shut up and calculate, you know, when the child asks you, you know, why is whatever, you know, you tell them eat your spinach. Shut up when you don't feel like explaining, okay? Because these guys don't exist. I don't really, I don't have to do it. They don't exist. They are gauge-dependent states. So the rule is you don't even try to compute them.
But you could put them on external lines, just so the matrix element will vanish.
Right. What could happen is that if you want to work in a more, how to call, covariant manner, it would happen actually that you make a mistake and produce them. This is what would happen, okay? This is because you could put them on the external state. And I think this is even more manifest in QED, so let's go there, I want to tell you. Because if you didn't worry, what I meant is, if you had not worried what happened in QED, then you shouldn't worry, you shouldn't bug me. If you didn't want to bug, you understand what I'm trying to tell you. It should have bugged you before. Okay, it's good, it's better late than never, but it should have bugged you before. And this is precisely from what you said, Julian. So let me show you there. Imagine that I want to calculate some black box that produces a photon. What will happen, you know, think of that. There will be a diagram like this always, right? That photon couples to spinors like this. There is gamma mu here, there is a conserved current, we'll say in the moment. So the amplitude, I could write as some mu times epsilon mu. This is what you do. And then I say, what you have to produce is the amplitude squared, and then you sum over all the possible spin states, velocity states of the photon, right? This is what you were doing. Now, this, by definition, there are 2 states, epsilon transpose. Let me call them 1 and 2, which we write as 1. Remember what we took, plus or minus I, 0, and we normalize. So what would I get? If I say I should sum on these states, then I will get 1/2 m1 plus I m2 square plus m1 minus I m2 square. Now these are directions 1 and 2 in the Lorentz space, and this is m1 square plus m2 square. And let's imagine the photon moving in the, why I took it this direction, I should have said the photon is moving in the third direction, okay, in the z direction. So k is equal to zk. And normally this is not how you work. I think this is maybe okay, I hope this is what you were asking me. Normally what you would do, you would write this as mu star, and then epsilon mu, epsilon u, and then some overall spins. You want to have some nice convenient Lorentz covariant way of computing. And remember what it is. This thing in QED is minus g mu nu plus some dependence on gauge, q mu, q nu over q squared. I don't even want to write what it depends. I don't care. Why? Because this does not contribute. The point is that, look to see what the amplitude mu is. Just to remind you, mu would be psi bar p2 gamma mu psi of p1 up to a coupling E. Well, let me write p2 p1. This guy moves with the. And by the way, this can be generalized to any black box. It's called a ward identity. K mu mu vanishes. Photon is always coupled to a conserved current. This is true in general in QED. And this is very gratifying because it tells us that these longitudinal degrees of freedom, time-like whatever they are, do not contribute. I can always go to the gauge in which they don't exist even, as Feynman did. So we are using the fact, and remember we checked it explicitly that q mu psi bar gamma mu psi is 0. This is a conservation of current in the momentum space. Right? Q mu is P2 minus P1 minus P2 mu psi bar P2 gamma mu psi P1 is 0 by Dirac equation. Okay? I showed you last time, but if you cannot reproduce it in 2 minutes, okay, then you go and check your knowledge of the Dirac equation. Everything in this course is based on SU2 group theory and knowing Dirac Lagrangian. If you know that, you just covariantize it. But if you know that well, then you know field theory, basically. I know I'm simplifying, okay? It's a tough subject, field theory, terribly tough subject, okay? But in a nutshell, you know, when I ask you what the crux is, it's that, knowing the Dirac and group theory. So actually, what is good? I should be supposed to work with this, which tells me that this is equal to m1 squared. So only this contributes, right? So this is, let me be specific, minus m0 squared plus m1 squared plus m2 squared plus m3 squared. If I do with this, I'm actually producing, I'm pretending that I'm producing extra degrees of freedom, okay, that's presumably what I'm being asked. But fortunately, you see, k mu mu is 0. What is k mu? K mu is k, 0, 0, k in this picture. In this direction that I took in this picture. So k mu, mu, when I write, is m0 minus m3. And this is 0. Minus m0 squared plus m3 squared. If you didn't want to use this nice covariant way of writing, you would have never even faced this question. And that's maybe why I didn't ask it, because you are strictly asked, just think of producing physical states. Because if you start asking what happens to the states that don't exist, then you know there are billions of states that don't exist. I can imagine them existing, okay, or maybe they belong to a new physics. I'm sure all of us agree there will be new physics. We don't worry about producing them if we cannot produce them. For whatever reason. So you see this? There is a cancellation, strictly speaking. If I want to use this covariant picture, if I propagate unphysical degrees of freedom, this is what I've done here. In this particular gauge, I would propagate. This would be equivalent to choosing a gauge. Remember, which was minus I in QED G mu nu plus psi minus 1 and so on over q squared if you simply don't take this. This is equivalent, okay? This is why Weinberg, this is why not Weinberg, it was not him, it was at Hoft later, but it was Feynman, was using this gauge because he knew that because of the current conservation, he didn't have to worry about that. So he could be nicely and simply.
But in the case of, like gauge Boson, massive gauge Boson.
Oh, we have to do that. We'll do that in a second.
Is it, the cancellation is.
Yeah, no, it's non-trivial. It's a little more complicated. But yeah, that will something similar will happen. I will have to cancel this guy against the other guy. I have now 2 extra degrees of freedom, fortunately. Okay, but this is how Stuckelberg actually got this brilliant idea. He was just too early. He was too much ahead of his time, and nobody paid attention. That simply like here, if you have 2 extra degrees of freedom, they may cancel. Also, they may give you the gauge freedom, so then you have a well-behaved propagator. Okay. So the issue that we are asking, I think now we can sort of be clear about the question that Urian asked. And that is, if I want to work like this, with a fully covariant, simple propagator, then I'm actually including unphysical degrees of freedom. I want to be sure that I'm not producing them. 2 ways of being sure. Don't do it. Simply don't do it. Just write in a non-covariant physical way of using only the transverse degrees of freedom, okay? But it's not easy to compute like that. It takes time. You prefer to write like this, notice. When I gave you, I'm sure in the homework, you would use these formulas. I mean, that's how I work. Unless, of course, I ask you, please compute the probability of producing this, which I did in the top 4 case, right? I ask you, please check that particular state. Then it's different. But if I tell you produce the W, then you sum immediately, okay? You save yourself a lot of effort and time. Just like if I don't specify the spin of a fermion that we are producing, then you immediately use the trace formulas, right? Sum of the spin is just P slash O plus N. But I want to make sure that you understood the QED case. It's always good to go back to the basics. Whenever a new question comes, go back and try to see what happened in an example that you did before. That's what it means doing physics. Try to use the language that you already mastered. It's funny that I have to say this, it's some kind of disclaimer. But as you will see, these days often the opposite is done. So that when you will go to seminars and people explain you that this is happening today in the Higgs physics because there are extra dimensions. And then you should immediately feel angry because how the hell, I don't even know what extra dimensions mean. There are no extra dimensions. Look at around you. There cannot be extra dimensions. There's no way. I may have some picturing which looks as if there are extra dimensions, but physically it will mean something else. But it's very dangerous that I use that language to explain something that I know. What I should do is to use the language that I know to explain something new. I don't use the new language to explain something old. Don't do that. Notice when you're learning a new language, you usually translate it to yourself in the language you knew, okay? I noticed the first thing I felt, I really, I started to feel at home in English. And my accent gives me away, I kept an accent, and I could see that I started to think in English. It seems I was calculating in English. I was using the numbers. There must be a moment when it comes to you guys, right? That's sort of a new stage. But previously, you go back. Okay, is this clear? You must sort of understand and forgive some of the preaching that comes out. I used to have longer hair and longer beard. And with this being gray, it comes natural. So we have exactly the same situation that we would have gotten here in the explicit way of doing it. If you tell me that you have it, I will erase it because I don't want to erase. And I don't want to erase the Higgs part, okay? The limitations of Blackboard force me to erase this as we just did. Okay. So what will happen in this case? You see, Jorge already anticipated it. He said probably what will happen that these two guys will cancel against each other. And to be clear, I have to go to the situation now psi equal 1. When psi is not equal 1, I can't even think of producing this guy. It simply doesn't exist on shell. If you wish, then you can carry on the same calculation, because notice that you have the same factor in both cases. So what I'm going to say now applies to the general case, but strictly speaking, I should address it for psi equal 1, in which it is not clear that the guy disappears. So with psi equal 1, you have you see d of g, and this is why it's confusing. It looks like a physical degree of freedom. I think it's really glad that you asked that question, okay, because this is where somehow something funny is going on. This looks like a perfectly well-defined particle, right, the original I started with. But it just tells me that there is a sort of fourth, or fifth actually, polarization, which is scalar. Okay, this belongs to this extra, because from in this case, this disappears. So what I notice that d mu nu, let's write again, just to make it clear, which is d mu nu proca, minus I q nu over ma squared, k squared over ma squared. So like plus I times minus 1. Which tells me that there is here I am summing, remember, over 3 degrees physical of the massive gauge fields. It has 3 spin components. So there is, let me write it epsilon 0, the time light. Now, number 4, which will be I q mu over ma. Then I will get it precisely epsilon mu star. You agree? I get an extra minus sign, but it's important that there is this vector I. I'm normalizing the same way I'm normalizing the other polarizations. Okay? We should normalize to epsilon squared. Notice that we normalize the epsilon times epsilon star was normalized to minus 1. So I have 2 extra polarizations, one scalar and one timeline. So if I am to calculate, so I ask myself the same question that I asked there, which actually I will now illustrate. I'm not going to prove the generalized word identity for the case of spontaneously broken theory. It goes into the category of what is called Slavnov-Taylor. It's not the theory, the symmetry is broken. The current is not conserved, remember. So let's illustrate this mu. I could ask the question for the black box. The amplitude would be mu epsilon mu. And so that m squared is sum of mu epsilon mu square sum over s. So once again, physically what you would do, if you didn't include these extra degrees of freedom, you would sum from 1 to 3. And you would have no problem. And now we said, let's sum from 1 to 3, and then I want to include this guy because somehow when psi is equal 1, but even maybe in general, I want to be able to work with this formalism and make sure that I don't make a mistake and produce somehow in a homework or whatever an unphysical degree of freedom. So what I would get here, notice, plus IQ mu, mu, well, it's actually, let me write like this. Sorry, let me be more careful. What I want to do, I want to write it as mu star, and then sum epsilon mu. That's why the issue comes, in which normally I would sum from 1 to 3. But now you say, well, what happens if I add this guy? I will have then there is an extra propagation with the minus sign. This is very important. I will get minus q mu, m mu star over ma squared from the inclusion of the, you agree? From the inclusion of the time-like component. There is an extra minus sign. There is also the fifth, which I could write as m phi, epsilon phi squared. This I treat separately, this is a scalar guy, but I have to include it. And normally you would never pose a question, okay, because you would stop here. But now that you pose it, what we get, I can erase this, I'm not going to need this anymore. So what do I get here? I will get that the amplitude square will be m square proca, the physical piece, the first three component. Okay, this is the proca. Minus the q mu over ma mu squared as a minus sign plus m phi squared. This is what I get. As before in the case, so see the time-like thing has this extra sign. This is what happens in the case of the photon. The sign was very important. The sign cancellation. So remember what we found in QED? In QED, the current conservation told us that M0 was equal to M3. So what we are going to get here, you can see immediately because you... Oh, I should have written it here. I wanted to keep everything on the blackboard, so I'm going to erase this propagator. The gauge interaction from the covariant derivative, in other words, from here, plus these charges, you get the gauge interaction, which is G, psi L bar, gamma mu, psi L, A mu. Only left-handed piece has a gauge interaction. Okay? As you know, happens in the standard model. Which means that mu is G psi L bar, gamma mu psi L. There may be factors of I or sine, I don't care, I'm taking the absolute value squared. So what is Q mu? Mu? We calculated it many times, right? I used the Dirac equation. There is a half here, so let's write down it's half G mu, sorry, Q mu psi bar gamma mu 1 plus gamma phi psi. Q mu on the vector current gives 0. Vector current is conserved. When I act on gamma phi, what do I get? We did it last time. I get mass. Twice. They add up. Here the mass would cancel from the Dirac equation because each time when I act with the Dirac equation here is the momentum P2, right? Here is the momentum P1 in the diagram. This is P1, this is P2, and this is Q. So this is simply up to the side. I don't care. I don't want to be careful. G M fermion. Why not I write over MA so that I have dimensionless here over MA, which I have over MA, and then psi bar gamma phi psi. See, plus or minus actually because it depends how you define your gamma. Or maybe it does. Because in both cases it's gamma 5. So I'm going to have a minus sign. Remember once we got minus m the other time. Or maybe not, I'm not sure. I'm not sure. It's irrelevant. This piece is equal g squared m fermion squared over ma squared psi bar gamma 5 psi squared minus sign. You see, in QED, once again, there was a cancellation between the timeline and the longitudinal here. Longitudinal is physical, it's very different, okay? There is no cancellation. Longitudinal went into the Broca thing, okay? What is cancelling this note is because what I call M5 is the, phi is just the interaction with this, the amplitude for producing the scalar mode. And this coupling, remember, is G MF over MA psi bar gamma 5 psi. Up to I or up to a factor, I don't care, up to whatever. I'm taking the epsilon value square. Okay? So that I will have manifestly this with a plus sign. The production of the timeline and the scalar piece cancel. See how nicely it's all worked out. You know, there was a precise coefficient 1/2. It was left-handed. It's the way I've chosen the charges. It all had, you see, all the conventions then disappear, okay, and then you get a physical result. There was a factor of half here, which was very important because you get twice the mass and so on and so forth. You don't really have to do it. You're never gonna worry about that. You have a nice covariant formula for the production of the physical states. That's the Broca. All you have to use that. This is just to set your mind at peace. To let you know that if you're making a mistake, if you're xi equal 1 and you don't see that it's a non-physical particle, okay, and then you include it and you say, well, I have all these 5 degrees of freedom, unfortunately they will cancel. The correct way of understanding arc psi gauge is actually to keep psi. That's really the crux of the issue, because you need to show that physics is psi independent. And then take psi equal 1 at the end of the calculation. But that's sometimes too messy. That's really a safe way to do it. It's very likely that you make a mistake. You know, you and I make mistakes. If you are not at Hoft, it's dangerous or Feynman to use. But you know, you have to weigh these factors, okay? So I must admit, I have not always worked in arc psi gauge. You know, hoping. What I do when I have very long calculations, I collaborate. I'm not at Hoft or Weimar. I've proven to myself, I've written some papers alone, okay? Just to prove to myself that I can do it. But it's, you know, 100 times harder when you have a, whatever you do, it's 100 times harder. There is, you know, collaboration means many things. One of the things that you can, you know, check the steps, of course. That hopefully you don't do on the final exam, but just stop to check. Anyway, maybe do. Okay. Tell me if I should slowly raise this. The minus sign came from the wrong propagation of the timeline. The timeline has an extra minus sign, both in QED and here. Okay, I started raising it, and let's see if the question pops up. once I do that, because you and I are, I spent a lot of time doing this, and in order to justify, we'll do a loop calculation. Something in which you don't have to renormalize. I'll give you a physical process. Let's think what we can do. You will see that there are a number of possibilities. If not before, surely on the final exam, so that you have more time to look into it. In which we actually see how you can compute in this gauge. But for the time being, when we are studying the physics of the standard model and trying to understand what goes on, let's forget that there is this G field. It will never pop out in anything that I do at the 3 level. And for the next 2-3 weeks, I can't speak of loops, obviously. We have to understand the basic physics of the production and the decays and the properties of the WZ and especially the Higgs. Okay. So this is where I stop. This is the picture of there is just a Higgs boson, one single scalar guy. And I asked you the other day, why is it that I had to wait so long to produce the Higgs? And I said, think about it. Why didn't they produce it immediately when they produced WZ? We'll have to talk about it. After all, we are not yet in the standard model, but... Huh?
Because of the...
No, it's not that heavy. It has, it weighs less than top quark. It weighs less than top quark. Top quark was discovered, in 96, I guess, 95, 96, 97.
Because of the cross-section, there is no...
Why? How do you know that without computing?
I mean...
Well, I should go to the global case, but I like these digressions a little bit just to wake us up from the technicalities, which are important, of course.
Backgrounds? Because it's difficult to find it because of background?
Because?
Because of the backgrounds?
No. No, once you produce the Higgs, well, you would have to worry how it decays. By the way, depends how much you're in a hurry. Eventually you will see beautiful decays. It decays into, Higgs decays into, well, it doesn't have enough mass, we'll learn today, to decay into ZZ bar. But 1Z can be off-shell. Okay, why don't we do that? I'm going to spend 2 minutes because I'm going to do another calculation. Okay, so before I do that, let's talk a little bit here. The gauge field you understood, right? The gauge field, where is it? Is coupled to a fermion directly with the gauge coupling. And remember, gauge coupling is not small. Just to bring you an idea, E, remember in the standard model I already derived that E is G sine theta W. Do you remember this?
Yeah.
So G actually, well, it's not the same G here. This is a U example. G is not small because G is bigger than E. But E is not small. E squared over 4 pi, which you learned is a number of order 1 over 100, depends of course on which energies, okay, so you don't have to know a precise number, tells me that E is of order 1/3. And G is even bigger. It's a half, it's of order 1. So therefore, when I produce a gauge field, how would I produce it? By scattering. What do I scatter? How did I see the W and Z? What was the original production? A short reminder here. He started with a proton-antiproton machine in 1983, in which actually, for example, W, you would scatter an up quark from the proton on the down bar, anti-down quark from the antiproton. And this will produce a W boson, you agree? The charges are precisely. This will produce a W plus. And the cross section is going to be proportional, and of course W will decay. So what I'm producing is a particle at resonance which decays into an electron neutrino or whatever. Okay, come back to it. Well, you computed decay. The cross section will be proportional to G squared, which is a number of order 1. And then kinematics factors, right? If I want to produce the Higgs, what can I do? I go where the Higgs is, how it's coupled, right? And how is it coupled? The same way that I do here, I can take, maybe it's more illustrative that I don't do W, but I do the Z. I take U, proton, U bar, and that proton, and I produce the Z boson, which is neutral. Again, the cross section for Z, proportion G squared. If I want to do the Higgs, there's going to be G, but there is also M fermion. This is what suppresses it. Quarks are light. Something that you have to take my word for the time being. Alexei didn't talk about it. You never asked me. What does he mean by quarks? Or mass of the quark? You must have talked about the mass of the quark. So you're asking, what the hell do you mean by the mass of the quark if I cannot see the quark? And it doesn't compute the mass, doesn't contribute to the mass of the proton. So what is it? It's a funny thing. Why do I talk about it? Well, I don't know why I talk about it. I have to talk about it. But at this point, what you have to know that it's small. M quark, up and down, is on the order of few MeV. It's terribly small compared to the mass of the Z boson. This is why you couldn't produce it. No hope, even at LHC. Later on, what you did was a, how do you call it, the lab machine, EE bar, same problem, even worse. The electron is light. So what do? How could you produce it? You have to produce it. We did produce it. For example, at lab. By the way, just to tell you, okay, 2 more minutes. At lab, they put a limit on the lower limit on the Higgs mass. Even just when they were about to shut down the lab, they said they were seeing some events that looked like Higgs. We never know whether they were seeing these events or they wanted to see them. You know, you imagine you spend years of looking for a bloody guy, and then they shut the machine on you, shut down. So how will I produce it? It's here. I mean, I wrote the Higgs coupling. So you see what I can do at lab, for example, E going out is equivalent to E bar entering. I can produce a Z boson, you agree? And I do. And they produced millions of Z bosons, 1 billion of Z bosons. And so we have all these beautiful detailed properties of the Z boson. You know, it decays to better than 1% and so on and so forth. But then, and this is what I want you to appreciate when we write this formula, okay, physics is hidden here. There is a coupling of the Higgs to the Z boson. Whoever gets the mass from the Higgs, we couple the way I've written here generically. I told you, if you learn the U1 case, this is going to be true in every theory in the world, whether it's SU5 or SO10, or whatever you can imagine a new superstring theory. It's going to boil down at the end that there is a Higgs guy who gives the mass to the particle, and it has to be of this form. So that means that I can produce, there is a coupling ZZ Higgs. Of course, one is off shell, this guy. And you know, it's very easy to see the Z guy. He decays very nicely, very recognizably. That's how they saw it. That's how they studied it, okay? That will decay into 2 fermions, whatever you like to see. It will decay into an electron again, or a muon, or a quark, okay? You guys computed the decay rate. And this guy also decays into fermions. And this is very clean at lab. It decays into electrons, okay, very little, okay. You can say, I'm not going, it's a small branching ratio, okay. But whatever the guys do, I will see it, you know, it'll be easy, okay. And they didn't see it. And the energy of lab was around 200 GeV. That was their limit. Maybe 205, don't ask me a precise number. This was the total energy at the left disposal. So they could put the mass limit on the Higgs. Tell me what it was. 110. Actually, it was 15, so maybe there was a little more here. Okay. I'll write, to be consistent with myself, using the fact that MZ is around 90 GeV. These are kind of issues that we are going to be studied at length, okay, in the physics of the Higgs, okay. We are going to dedicate a couple of lectures to get sort of an inside-out picture of its physics. Imagine how close they got. Life is not fair. Then come this guy at LHC, you know, get all the praise. Everything was understood before. LHC didn't have to do anything. All the physics of the production, of the rates and so on, this was understood long before. And by theorists and experimentalists, they came very close. And Tevatron came close, okay, a new machine and Fermi-like, but not enough. So that was a little digression.
Question.
For those of you that want to understand the physics and not just the technology of, yes, please.
Why is it that they couldn't find the Higgs if they were like up to 1 keV?
Well, it has to do now, it's not just the energy. Here the reading of the property of the Higgs is very easy, okay? So here all you have to add the energy. But it's not enough to have the energy, it's necessary to have the energy. There is something that we call luminosity, and the way of you identifying, okay, you have to produce enough states in order to be able to find. I'll have to come back to it. You see, the E plus E minus machines are very clear, they are trivial. They're very clean. The problem is that you limit the energy. And it has to do with we'll talk about it, with the radiation loss and so on, okay. We'll do it more seriously, okay. Just wanted to wet your mouth. And at this point now, I want to pretend that I am in a global situation, that there is no gauge field. I want to spend another half an hour talking about the global case, okay. I want you to understand the physics of the Goldstone boson, Nambu Goldstone boson, this one guy. If you understand this one guy, it doesn't matter that in a big group I get 20. It's always of the same form. So what we said, that this guy has a coupling which is minus phi m fermion over V G psi bar gamma 5 psi. Right? Everybody is clear on this? Now, what is this coupling? You say, this is new. I know what psi bar psi is. What I mean, I know what psi bar is when I go to low energies. How do I understand what is happening? I go and use my experience with low energies. After all, this is how I came slowly to higher and higher energies, okay? So in order to see where it is going, let's go to the non-relativistic situation of small momentum. To appreciate what kind of physics I would produce. Why? Oh, I should stress that mg0. Oh, it's here. I don't have to write it again. The mg, I put it there. I don't need this properly. Then mg0. What kind of potential it would produce? If I exchange this G guy at low energies, what kind of potential do I get? We've done that. Let's see if I can use this chalk. Maybe I have What would be the potential of due to G? It will be this coupling square at least this suppression times 1 over R. A massless particle, we derive that. When it's massive, we get Yukawa potential e to the minus mr over r, and the limit m going to 0, you get the fatal thing that you get in gravity, and the same thing that you get in QED. the 1 of the R potential. Then you can tell me, well, but this is just like gravity. I'm writing gravity in the form that we like to do. G Newton is 1 over m squared, so we put it. And Planck go. So you can tell me, oh, but boson cannot exist. We know how gravity looks like. We know what the long-range behavior between two bodies is, and we checked it at distances, even below millimeter. You know, they do experiments all the way to galactic sizes. We have very good knowledge, but especially in the laboratory, you know, at the distances of, I don't know, 10 centimeters per meter, you have these Etwish-like experiments in which you probe the nature of gravity, and looks good. There is no fifth force. This is a new force that will propagate at all distances, okay? So why is it when I look at at Sun and us, why doesn't Goldstone boson modify this famous gravity force? Okay, would be the right question to ask. Now, just to give you an idea, to understand what is going on, M Planck is about 10 to the 20, 10 to the 19, which I will take for the sake of, you will see huge numbers around 10 to the 20. To give you an idea, if I take two protons, this force, the mass of the proton is MeV, so the strength of gravity is about 10 to the minus 40 times 1 over R. So look at this guy. This is M fermion. Let's take, well, I don't know what you like, electrons. This will be MeV. Let's take some scale. Okay, I don't know what V is. This is not the standard model, okay? So I'll take V to be something bigger than 100 GeV. It's bigger than the physics today. Just to give you an idea, if I took the standard model, what would I get here? If it's 100 GeV, MeV, this is 10 to the minus 10 roughly. 1 over R for this. 30 orders of magnitude bigger, right? So you start being worried. And it's proportional to the mass. So you say, oh, but look, if I look at the star like Sun and Earth, then I'm going to get a huge coupling. Because why is gravity is big? Okay, to understand why gravity is, why does gravity matter? Why does matter gravitate? Okay, after all, I show you it's non-existent there, but yet the only force that exists really at large distances, basically, in the universe is gravity. So why does gravity matter? Sorry to play your words, why does matter gravity? Because there are a lot of particles.
Because it doesn't.
Because?
All the mass.
It accumulates, right. Because Earth, for example, how much mass there is in Earth, okay? I don't care in kilograms. How many protons in Earth? It's about 10 to the 50. I think it's 10 to the 51. And Sun? You know the ratio masses of Sun and Earth? I had to look it up, I always forget. Okay, I had a rough idea.
1 million times.
1?
Million times.
Mm-hmm. It's good. It's between 100,000 and million, okay. I always remember million. It's actually maybe closer. Maybe it's 350,000 something. I'll take a million just for simplicity. Billion is easy to. So this is in Earth and in the Sun. Okay, so Sun would have, well, look, let's not worry about 5 orders of magnitude. I know that in the celestial object, look at the scale of this number. Sun is not much bigger than Earth from the point of view of these protons, okay? So look at the Sun, Earth. the force is 10 to the 100 over r. No, 10 to the 100 over 10 to the 40, sorry. Why? Right, the same. Right, I don't forget G Newton squared. So I get about 10 to the 60. It's the dimensionless coefficient over r. Agree? It's huge now. But you were worried that maybe this will accumulate because this is also proportional to mass. So let's understand. I'll come back and I'll write this number again. Let's see more carefully what this really is, because of this gamma phi, I don't know what this is as a coupling in a non-relativistic limit. Psi bar, gamma phi psi, is psi dagger gamma 0, gamma phi psi. This is psi dagger. This is off diagonal phi. Notice it doesn't matter what convention I use for gamma 0, gamma phi, okay? This is very important. This is how physics enters. Sometimes you like to take gamma 0 off diagonal, relativistic case, and gamma phi diagonal. You can do vice versa. I mean, after all, they have the same properties. The square, they one, they anti-commute with the others, okay? The product would be off diagonal. And it is. And let's write psi as uv. So what is it? Well, let's be careful now. This will be at momentum P2 and the momentum P1 in general, okay? I want to see what happens when I take this coupling. What do I get? I will get here U dagger P2. Well, why don't I write? I'm trying not to write, but maybe I should. U dagger, V dagger at P2. And then I will get, because of the sign, what will I get? Minus V U at P1.
Yeah.
Correct?
Yes.
So I'll get U dagger P2 V by 1 minus U dagger minus V dagger P2 U pi 1. Something like this. Okay, up to a sign. But what is the relationship between U and V in non-relativistic limit? I have to go to non-relativistic limit to see what the potential is, right? I want to see what happens when particles are moving very little. Okay, which is the situation that you will see corresponds to the relevant physics. So you remember non-relativistic spinors?
The completely decoupled.
In non-relativistic case, it's convenient to take gamma 0 to be diagonal. You forgot it. Well, you can do it any which way you want, but I want to be in non-relativistic case, so I'll take this. And then I have this equation P slash psi is equal M psi. So I get E, okay, I remind you, E, right, gamma 0, look at what I take, this will be Z, minus sigma dot P, sigma dot P, minus E, UV, is M UV. Note, look at the second piece. I get sigma dot P U minus EV equal to MV. This one is more useful than the first thing because E is very close to M. Actually, in the non-relativistic limit, I can just keep the first term. Okay, E is M. And then a small correction. So I will get immediately here a famous result that V is sigma dot P over 2mu. As you know, when you go to another physics case, there is only a two-component spinner to talk about. That's spin. I don't need this four-component, okay? But why do I have four-component? Why do I have a four-component Dirac particle? Because I need to talk about electron and positron. After all, they can be produced at high energies just by, photons scattering on the cells. Okay, I can create them. So I need a four-component spinner. Tells me that I have both electron and positron inside. And I often speak of left-handed electron and right-handed electron, but what really I mean is a left-handed electron and a left-handed positron. Remember under charge conjugation? Left and right to get interchanged. So you can think like that physically, okay? The doubling of degrees of freedom is because actually they are doubling of states. But if P goes to 0, V will disappear and I will have a two-component spinner, which is what we used to do. So what I have here, this is then proportional, you can convince yourself, to U dagger sigma dot P2 minus P1 over 2mu. This is how the Goldstone boson interacts. It's U dagger sigma U Q over 2m. Okay? So I borrow some space, or maybe let's just forget the Higgs. It's time to wrap it up. Let's not talk about Higgs today anymore. So then what I have is the decoupling of Goldstone, which was M fermion over V psi bar gamma 5 psi, actually in the non-relativistic limit turns out to be something I can deal with. M will cancel, right? There'll be Q over 2V times U dagger sigma U G. What is this? Spin. So G couples to Q over V times spin. This is a crucial property. This is very important. It tells you that this guy cannot compete with gravity because spin is a vector-like property. It does not accumulate. If you look at large nuclei, they have a spin of order 1, between 1 and 10, 5 maybe. Why? Because it's a vector. So there'll be this, and there'll be this, and there'll be this. Okay, the sun has small spin of order or whatever is a number, 1, 10, I don't care. It's not 10 to the 50. Masses accumulate. You see, in the case of a scalar interaction of a spin 2, you will get psi dagger psi, which will be U dagger U. And that would accumulate. There will be no spin suppression. So let's see what it is. What will happen really? You can say, well, take the zero momentum. Well, stars are hot. Even Earth is hot. Okay, not here. Well, it's becoming now, even on the surface. Okay, not really hot. Okay. But it's sort of hot inside. But stars are even hotter. So this coupling really, if you think of a star, the guy coupling is the average momentum will be on the order of temperature. You agree? That's the only scale. When the temperature is big enough. So it will be order of the temperature over V times spin. And that's GT over V. So you see, if I look at the celestial object, I will get something which is the order of T over V squared times 1 over R. Whereas here I had a number which was 10 to the 60. This number is always less than 1. The temperature of sun, for example, do you know what the temperature of sun is?
15 million Kelvin.
It's about MeV, I think at most. Is that correct, the way you remember? Maybe even less. You remember it as millions of keV? Tens, 100 million keV?
Something like
keV is about 10 to the minus 3-4 electrovolt. It's even less. But okay, I know the temperature is less than MeV. See, particle scale is huge physics. This is why we cannot dream to see the temperatures that correspond to particle physics of today. The scale of the standard model is 100 GeV now, the relevant physical scale in which the dynamics takes place. Okay, this is why we cannot check the dream of checking the phase transitions that may occur when I heat up systems like our vacuum, because even stars that are extremely hot are completely cold on that level. Right? So obviously this is a number which is much less than 1. You're supposed to compare it with 10 to the 60. Okay, Goldstone bosons are innocuous. They can pose no danger. They are actually not a new force. It's true that they propagate very far, but so feebly. I can completely forget them when I talk of stars. When I speak of 2 protons, actually this guy will dominate as soon as they move a little bit. So 2 protons inside the stars, Goldstone boson wins. There is something to worry about. I can't pretend that they provide no dynamics, okay? And this was one of the first nice examples of astroparticle physics. In the late 70s, people said, aha, how will I put the limit? What can happen that can be dangerous? Okay, it cannot give me new force. I'll come to your question. It cannot give me new force, but it can do some other damage. These guys will be produced in a star. You agree? Depending on the mass, okay, this may be the temperature-dependent piece or mass, okay, they will be produced, and what they do actually, they would cool the star off. So maybe I'll let you put the numbers. Maybe I don't do it today. You can actually put the limit. You can take the following thing. You know that sun shines. Well, yesterday was clear. This morning, not as clear. Sun shines. Therefore, it didn't cool down yet. We can relax, right? It's going to take some time. It's going to cool down, unfortunately. It's going to take some billions of years. Sun shines, and that means I can put a lower limit on V. This coupling must be very small. Because if I produce this Goldstone boson, I start cooling the star too quickly. And it would have been happening throughout the history of the sun. So I won't give you the details, but you can prove that T is huge. This physics of Goldstone boson does not belong to the standard model scale. It belongs to astronomical scales far, far from any imaginary collider. See how important is this marriage between cosmology and particle physics. You can set up, because you can go and say, oh, let me look for this Goldstone boson, here, in the lab. Well, you can do that. You won't find it because I can prove to you that the scale has to be large, because even if I produce little by little, the effect will accumulate. Even if the coupling is weak, I'll be continuously producing it. And that's bad for us, it will be bad. You had a question?
Yes, I was thinking like, I mean, when you have a spin, sometimes, there are some potential for some also I mean, it doesn't matter. You, for example, you have ferromagnetics that after a phase transition, they have domains, both, I mean, domains that where the spin
Sure.
points in one direction and the vector, I mean,
Sure.
accumulates and
Yeah,
then
of course.
they have like a, I don't know,
Of course.
force. I don't know, I was thinking like maybe you can test this G on, like on, I don't know, like also like in...
Well, the temperatures are very large. You see, the temperatures that become to be relevant, you see the scales of particle physics. What do you do with a scale of 10 to the 9 GeV? It's so huge. So in order to see, even the standard model, forget this, think of the standard model, which is very interesting. Suppose there had been a phase transition, Jorge is asking. If the universe, if it is true that when I heat up the system there will be a typical phase transition, that means that the temperature much bigger than V of the standard model, which is on the order of 100 GeV, after all WZ masses, top quark mass. At this temperature it means that I will have phi equals 0. So when the phi is turned on, would it be pointing in one direction or it will be pointing in different directions? I could get domains. This question is interesting if, for example, if you have additional symmetries like discrete, even more interesting. They are particularly interesting because then you really know that you get these domains, stuff like that. But in order to address this question, and these are beautiful questions, the behavior of spontaneous symmetry, broken symmetries at high temperature is a wonderful subject. And you would expect, for example, to get domains with discrete symmetry. You could even speculate that in one domain the world would be maybe left-handed and the other would be right-handed if parity is broken spontaneously. You know, inside the domain, of course, left is defined. Or maybe one domain would be matter and the other would be antimatter, depending how CP is broken and so on. Okay, when we learn more, I can come back to this issue. It turns out the domains, unfortunately, would be very large. People used to ask this question, where are the anti-baryons? Where is antimatter? How come he's made of matter? You know, I've just proven. Well, I should have known. He shook hands with you guys, right? This is very strange because we would sort of expect a symmetric universe. There is a field which is called baryogenesis, which deals with this issue, which tries to understand why the world is made just of matter. And apparently, you know, we know that Venus is made out of matter. You know, you can send something, Mars, you can, and then you can have indirect tests. You can imagine, because if there is matter and antimatter, they annihilate, so you will see this annihilation. So we know not only that our galaxy is made out of matter, even apparently a cluster of galaxies. So the question is a little less exciting than it sounded originally because the size of the domains keeps growing by not seeing interesting. I have to think of some domains of different physical properties. However, it's fascinating, even if you cannot reach these temperatures. It's a nice subject. It's even a question, is this always happening? Do the symmetries always get restored? Okay, a little anecdote. I used to like, for obvious reasons, my first paper was to show that parity can be broken spontaneously. I like this idea of TDL that also CP can be broken spontaneously. So if it's true that the symmetries are broken spontaneously, then when I heat them up, I will restore the symmetry. But for example, if you like baryogenesis, then you need the CP to be broken, you know, in order to say that there is more matter than antimatter. There can be no CP symmetry because CP says matter equal to antimatter. So if CP is good, if you produce 5 baryons, I guarantee you will get 5 antibaryons, no matter what you do. So you got to break CP. So the question that was interesting question that we were studying with Mohapatra some years ago, 1979, I'll never forget. Just by playing, there was this question that, you know, your symmetry gets restored, okay? And you start playing on a paper, and we found some counter-example, it seemed. We found something that looked at the symmetry didn't get restored. But you see, restoring of symmetry, what it means, you have this vacuum expectation value, for example, a discrete symmetry. Okay, I should stop, I never... trouble to stop. plus or minus V. But I got to say a few more words. Okay. Hopefully not boring. So you see, when V is non-zero, you are sort of ordering the system. If phi is 0, you have less order. Here I'm pointing a direction, just like if I point direction in the ferromagnet. So obviously we say, but look, the entropy tells you if you go to higher temperature, you get more disorder. So even without doing any calculation, you say, look, when you go to high temperature, forget that phi is going to be 0. And that's what people told us. We talked to some distinguished physicists, okay, and for a year we couldn't publish our findings. And then it turned out, this was 79, that in 1974, Weinberg wrote a classic paper. I really hated it because this is the most original idea that I ever got, or the result. And then it wasn't original, okay? You hate that. It turned out, and it was so original that most people, excellent outstanding physicists, I don't have to name them, told us that we were basically stupid. We didn't understand thermodynamics. We were getting. And Weinberg, actually, it seems that Coleman told him of a system in nature which is called Rochelle salt. Salts, when you heat them up, they melt. You see, because crystal is order. When it melts, it's less order. Rochelle salt, when you heat it up, starts getting more and more order. Eventually it breaks down. Eventually the physical argument wins. But not very effective. That's all we needed. It turned out we were right. There are counter-examples to this. But he had Weinberg. Weinberg knew it, actually. So we could publish our work, which was less exciting. We had to cite Weinberg, okay. That was painful, okay. We could apply it to what it is, but it's terrible. First you think that you are wrong, people kill you. Then you prove to yourself that you are right. And then it's not original. 5 years before. That will happen very often. By the way, most of the time you will discover something, and most of the time your advisor will show that you are wrong. Okay, forget it. So think twice when you go to run excitedly to your advisor. Okay, check it. Okay, because most likely it's going to be a 0 that you didn't see. But occasionally you may be right, and you may be excited, and you may even write a paper. And then. See, these days it's easier to find the temperature. The literature, sorry. Because you can put these catchwords, and it's very likely that you will find it on the web, right? Okay, sorry, little digression. But I find this very important. And this subject has to do with I will mention this from time to time, the physics beyond the standard model that I find very exciting. And the one is the cosmological applications of symmetry breaking and the existence of so-called topological defects. Domain walls and stuff like that, domains, strings, there are funny things that magnetic monopoles, it's all related to this issue, okay. Okay. Okay, Wednesday, then I'll turn now to some group theory, okay? Some of it you already done at the homework level, okay? We'll just be a little more systematic about the example that you're finishing up. It would be much better if we do the homework by Monday morning. I mean, after all, Monday you're busy. Maybe we should think, okay, start it sort of because I gave it on Tuesday, because then on Monday I could discuss that. It'd be very useful, okay, when it's hot and fresh. Some informal question. This will be on the safe side. Okay.
You did it. You did it. Oh, it's still on. Still on.